Good day, esteemed members of the panel, our research advisor, and to fellow students. I am Joyce Anamnamedes. Today, our group will present a study that explores the very heart of the STEM experience, the intersection of failure and discovery. Our research is titled Trial and Error, the lived experiences of grade 11 STEM students with failed laboratory experiments.
In the science, technology, engineering, and mathematics strand, laboratory work is the primary bridge between abstract theory and physical reality. However, while the scientific method is fundamentally a cycle of trial and error, the high-stakes academic environment often stigmatizes failure. At Katagtagan National High School, we identified a significant research gap while existing literature focuses on successful laboratory outcomes. There is a lack of documentation regarding the lived experience of the struggle itself. This research aims to fill that gap by redefining those failures not as endpoints, but as essential pedagogical tools.
The central problem of our study addresses the lack of documented lived experiences regarding STEM students navigate their emotional and technical fallout of failed experiments. We specifically look at, first, the primary causes of laboratory failures, distinguishing between human and systemic limitations. Second, the psychological and cognitive impact of students' academic self-efficacy. Third is the resilience strategies used to transform failures into learning outcomes.
The significance of this study lies in its ability to humanize the STEM curriculum. By understanding these trial and error experiences, we can help educators create a more supportive environment that fosters a growth mindset. This is crucial because in the professional scientific world, failure is often the first step toward innovation. Our study is unique because it situates this phenomenon without our local institution, highlighting how resource-specific challenges like those in our laboratory affect students' persistence and problem-solving strategies.
Our research is anchored on Kapor's theory of productive failure, which posits that the struggle to find a solution leads to a deeper conceptual mysteries. We also lean on Kolb's experiential learning cycle and Garmes's resilient theory. To the panel, these theories allows us to see failure not as a lack of intelligence, but as a necessarily cognitive conflict, a mental state that forced the students to reconcile what they knew with what they just observed. This framework explains why students who fail actually develop a more robust understanding of the scientific method than those who succeed on their first try.
For our methodology, we utilized a qualitative phenomenological design to capture the essence of the student's experience. We interviewed 17 grade 11 STEM students through purposive sampling. We chose 17 because we reached data saturation, the methodological point where new interviews no longer yielded new themes. Ensuring our data was exhaustive, we also employed bracketing, where we as researchers intentionally set aside our own biases as STEM students to ensure the themes emerged strictly from the participants' authentic voices, R1 to R17.
Our data reveals that failure triggers an immediate and heavy emotional response. Participant R4 stated, "I felt a heavy sense of disappointment, making me question if I actually understood the lesson." This highlights a critical finding for STEM students. Laboratory accuracy is not just a grade. It's deeply tied to their academic identity. We observe that this initial emotional trial acts as cognitive unfreezing. While the frustration is acute, it is this very discomfort that motivates the students to transition from passive following to active investigation.
We found out that failures is rarely simple, or the result of a single mistake. They are a combination of environmental noises, limited equipment, and procedural misunderstandings. RE16 mentioned how lab noise disrupted their concentrations, while R8 noted that older equipment made precision difficult. This proved that trial and errors often result of external systemic factors beyond students' control. These findings suggest that school-based failure is often technical error rather than conceptual error, requiring students to develop high troubleshooting skills to overcome environmental hurdles.
Theme 3. The turning point of productive failure and resilience. This is where Kapos' theory is physically manifested in the Lab 37 shared. We learned more by trying to fix the mistake than we did by just reading the manual. This is a pivotal finding. When an experiment fails, the student is forced into a debugging phase. During this phase, they must analyze every variable and step. This process builds resilience, as seen in participants who consulted peers and instructors to find a resolution. Particularly, this validates the use of reflection logs, graded activities where students earn credit for their analysis of failure, effectively turning a wrong result into correct scientific thinking.
In summary, our research concludes that the laboratory failure at Katagtagay National High School is a mandatory rite of passage. It transitions students from being passive followers of manuals to active scientific thinkers. We conclude that the trial and error process is the most effective way to build the resilience and technical rigor required for future STEM careers, as it prepares students for the actual nonlinear nature of scientific discovery.
Based on these findings, we offer the following recommendations. For students, views errors as data to be analyzed, not as defects of a character. For educators, provide buffer time for repeated trials and utilize guided inquiry. We recommended turning failed trials into reflection-based learning, where students earn points for troubleshooting accuracy. For the school, upgrade laboratory facilities to minimize technical errors beyond the student's control, such as environmental noise and equipment calibration.